we've looked at rotational kinematics, we've looked at center of mass and moment of inertia and torque. Now we're going to put all of this together into rotational dynamics. And all dynamics means really is forces, but because we're dealing with rotation, we're going to be looking more at torques. So when we deal with forces, we're looking at Newton's 3 laws of motion. If you remember, Newton's first law just says that if something's moving at constant speed or not moving at all, in other words, if there is no acceleration, then there is no net force. Things that are in motion stay in motion, and so on. So there's not really a rotational equivalent of that one. And then Newton's third law tells us that there are equal but opposite forces. There's also not a rotational counterpart to Newton's third law, but there is a rotational counterpart to Newton's second law. So let's look at that. Newton's second law for rotational motion tells us essentially that torque equals moment of inertia times angular acceleration. So the formal definition: an object that experiences a net torque about the axis of rotation undergoes an angular acceleration. This is very similar to Newton's second law. F equals ma. It's just with all of the rotational counterparts. So torque, which is the rotational counterpart of force, moment of inertia, or rotational inertia, again, same thing, which is the rotational version of mass, and angular acceleration, which is the rotational version of acceleration. So F equals ma, Newton's second law with rotation, is torque equals I alpha. And the link between rotational dynamics and rotational kinematics is acceleration. So just like this acceleration here was how we were able to use the kinematic equations, the angular acceleration is how we'll be able to use the rotational kinematic equations. Before I move on, if you are interested, I will show you how this was derived from this. If you're not interested, you don't need to know it. You can skip ahead until I get to the next slide. But if you're interested, I do want to show you how we come up with torque equals I alpha. So we know that F equals mass times acceleration. We know that acceleration is equal to the radius times alpha. So F equals mass r alpha. So substituting that in. We also know that torque is equal to force times the radius, and assuming it's a perpendicular, then it would just be sine of 90 degrees, which is 1. So torque over the radius equals force. Substituting this in for force, we get torque over radius equals mr alpha. I'm going to multiply both sides by r, so we get torque equals mr squared alpha. And for a point mass, if you remember, moment of inertia was mr squared. So this mr squared becomes I. Torque equals I alpha. So just by doing these rotational substitutions, really it's 1, 2, 3, we're able to derive from F equals ma, torque equals I alpha. Okay, net torque. So Newton's second law told us that net force caused an acceleration, and net torque is going to cause an angular acceleration, and it's the same idea as net force. So net torque is the sum of the torques due to applied forces. So you might see T net or sigma T. And again, all that means is that you're summing up all of the torques. make sure that you're careful of signs. So a counterclockwise torque is positive, clockwise torque is negative, and you do need to be careful that you're putting those signs in when you're summing the torque. So unlike our force diagrams where you're able to just take right minus left or top minus bottom, with your torque diagrams, so remember it might be a straight line and you're looking at various forces. Let's say the pivot's over here. You're looking at various forces where there are and what type of torque they're causing. Then you need to be careful of what way they're rotating. If you have, say, a circle that's rotating, then you still need to look at the direction of the torques to see what way they're causing the object to rotate. So do be careful of your signs. So we have our rotational kinematics and linear kinematic chart. I'm going to make another one for dynamics, just to show you how they're related to each other. We know that net force, units are newtons, is F net, or sigma F. Net torque is tau net, or sigma tau. Mass, variable is the lowercase m, moment of inertia, variable is a capital I, and then acceleration, we have a lowercase a, angular acceleration alpha. And paying attention to the units, force is measured in newtons, torque is measured in newton meters, mass kilograms, moment of inertia kilogram meter squared, acceleration meters per second squared, angular acceleration radians per second squared. And again, I'm going to write this. Newton's second law, net force equals mass times acceleration, rotational, net torque equals moment of inertia times angular acceleration. Okay, steps for solving rotational dynamics problems. Not that much different than what we were doing with forces. First thing you want to do is model the object as a simple shape. In other words, figure out what shape it is. Is it a circle? Is it a rod? And where the pivot is. You're going to draw a picture, define coordinates and symbols, and list the given and find. You also want to be drawing the torque diagram here. Figure out where the object rotates, the axis about which the object rotates, so that's identifying your pivot point. Identify the forces and determine their distances from the axis. You want to calculate the torques caused by the forces and find the signs of the torques. So once again, can't emphasize this enough. Counterclockwise is positive, clockwise is negative. Figure out the moment of inertia if it's not already given. So you don't have a formula sheet with the moment of inertias. I will make sure that I am giving them to you. Most problems that I've seen are either giving you the actual value for moment of inertia or the formula to find it based on what shape it is. And then the last part, you're going to use rotational kinematics if you need to figure out anything kinematic-wise, so position, velocity, or acceleration. So you've done plenty of problems like this. You've been doing them all year. We're just going to now be doing them rotationally. I'll do 2 examples. If you only want to watch one, then that's fine. If you want to see both, then you can watch until the end. A flywheel has a moment of inertia of 15 kilogram meters squared. A torque of 50 newton meters acts on it in the clockwise direction, while a frictional torque of 5 newton meters acts on it in the counterclockwise direction. We're looking for 3 things. First, the angular acceleration. Next, the time it will take to go from rest to a speed of 70 radians per second. And finally, we want to know how many revolutions it makes while speeding up. Okay, so first let's diagram what this is. This is a flywheel, so this is going to be a circular object. It's rotating 50 newton meters clockwise and friction going counterclockwise, so we're going to assume this is mostly rotating in the clockwise direction. List what I know before I draw the torques on there. So we know that the moment of inertia I is 15 kgm², that there is a torque, I'm just going to call that T1, of 50 Newton meters, and that's in the clockwise direction, so that will be negative. And then we have a frictional torque, I'll call that T2, equal to 5 Newton meters. And because this is counterclockwise, it's in the positive direction. So if I draw these forces on here, so we have a T1 causing it to go clockwise, call that T1, and then T2, it's going to be smaller, acting in the counterclockwise direction. Okay, so part A, I guess I should list what we're looking for first. We are looking for angular acceleration, time, and delta theta. So part A, we're just using Newton's second law for rotation. Net torque equals I alpha. So net torque would be T1 plus T2. That equals I alpha. T1 plus T2 over I equals my angular acceleration. Negative 50 Newton meters plus 5 Newton meters over 15 kg², equals angular acceleration. So negative 50 plus 5 is negative 45. 45 divided by 15 would be negative 3 radians per second squared for my angular acceleration. Okay, the next two problems are rotational kinematics. I can add into my given that my initial angular velocity, starts from rest, is 0 radians per second. My final angular velocity is 70 radians per second. So for part B, we're looking for the time. I'm going to use omega final equals omega initial plus alpha t. Omega final over alpha equals t. 70 radians per second divided by, I'm going to assume this is actually a negative 70 because it's moving clockwise. So negative 70 radians per second over negative 3 radians per second squared equals the time. 70 divided by 3, 23.3, keeps on going, seconds is my time. So time is about equal to 20 seconds. And then part C is asking us for the number of times it rotates, so it's asking for the angular displacement in revolutions. So for part C, delta theta equals 1/2 alpha t squared. We could have also used omega final squared equals omega initial squared plus 2 alpha delta theta. Either one's going to get us the same answer. I'm just going to use the first equation. So delta theta equals 1/2 times negative 3 radians per second squared times the unrounded 23.3, keeps on going, seconds squared. This equals negative 816.6, keeps on going, radians. And again, this is just negative because it's a clockwise displacement. We're looking for the number of revolutions though. So we're going to divide this by 2 pi radians per revolution. And because revolution is just a number, I can ignore this negative right here. So 816.6 repeating divided by 2 pi equals 129.9, keeps on going, revolutions. So delta theta is about equal to 100 revolutions. If you felt comfortable with basic Newton's second law problems, and then when we added the kinematics into those, then these are the same thing. They're just dealing with rotation. I'll do one more example if you want to see it. Otherwise, we'll just work on more of this in class tomorrow. A uniform disk has a radius of 0.4 meters and a mass of 20 kilograms. Two forces, one of 90 newtons and one of 125 newtons, are applied to the disk as shown. If the disk is initially at rest, determine the speed of the disk after 4.5 seconds. Okay, so this one already gave us a picture. Let's just list our give and find. Okay, we know that the radius of the disk is 0.4 meters. Mass of the disk is 20 kilograms. Force 1 equals 90 newtons. Force 2 equals 125 newtons. And the time is 4.5 seconds. Given that, we are looking for omega final, so the speed of the disk after 4.5 seconds. Okay, so in this case, it already showed us our picture. I'm just going to redraw it so we can identify the torques a little more easily. So we're going to have 125 Newton force. That's going to cause a clockwise motion. And then we have a 90 Newton force causing a counterclockwise motion. So let's figure out what these torques are. Torque 1 is going to equal 125 newtons times 0.4 meters, and the angle is 90 degrees, sine of 90 is 1. So this equals 50 Newton meters, and because it's moving in the clockwise direction from that torque, it's going to be negative. My second torque, T2, is 90 newtons times 0.4 meters. 90 times 0.4 would be 36 Newton meters. This one is positive because of the counterclockwise motion. So adding my torques, net torque equals negative 50 Newton meters plus 36 Newton meters. Negative 50 plus 36 equals negative 14 Newton meters. So I have my net torque. Okay, next thing, it doesn't give me the moment of inertia, but it does tell me that it's a disk and that it has a radius of 0.4 meters and a mass of 20 kilograms. So knowing that it's a disk, moment of inertia of a disk is equal to 1/2 mr squared. So this equals 1/2 times 20 kilograms times 0.4 meters squared. And I would give you what the formula is for moment of inertia for each shape. So I would have given you something like this. So half of 20 is 10. 10 times 0.4 squared leaves us with 1.6 kilograms meters squared. So now we can use Newton's second law for rotation. Net torque equals I alpha. We have I, we have net torque. So net torque over moment of inertia equals alpha. Negative 14 Newton meters over 1.6 kilogram meters squared equals alpha. 14 divided by 1.6 gives us, negative 8.75 radians per second squared. The only reason this angular acceleration is negative is because it's accelerating in the counterclockwise direction, so it's getting faster in the counterclockwise. So we're not looking for angular acceleration in the end. What we're looking for is final speed. So now it's time to use rotational kinematics. We have time, we know omega initial, and we know angular acceleration. So omega final equals omega initial plus alpha t. So this just equals negative 8.75 radians per second squared times 4.5 seconds. This comes out to negative 39.375 radians per second. So final angular velocity with 1 sig fig is about negative 40 radians per second. Okay, so a little bit different than the last one in that you had to find moment of inertia and you had to find net torque, but again, nothing overly complicated. It was just a few extra steps.